In module 3, we shall start with the design of a general purpose industrial helicate gear reduction unit, and in module 3 is the part 1, and our first lecture will be on gear unit design, selection of stage ratios, pinion and gear tooth numbers. So, in this lecture, first of all we shall learn about what is a gear reduction unit. Next, we shall consider a typical design problem. Next, the constructional feature of gear units. Steps in design will come next, and then finally, selection of stage ratios, pinion and gear teeth numbers. Now, what I have shown here, a typical general purpose industrial gearbox speed reducer. What we find here, say this is a shaft and then here is a pinion and it is mating with a gears, and then in the same shaft there is another pinion which is meeting with another gears. If we consider their base circle and then we can imagine that cross bell drive, so definitely this will have reduction here, that means there will be reduction in speed and increase in torque, and that will be further, the torque will be further increased by this one. Now, for this gearbox, so this is input first stage and which is helical gears. This we are going to consider the helical gears. So, this is helical gear first stage, and next we shall design the second stage also, which is also in this case helical gear. Now, this is a simple gearbox we have considered, reduction gear unit we have considered, but there might have more stages. That means, in this case there will be another pinion, then another gear here, and that may be connected to output or further reduction will be there. Commonly you will find that depending on the transmission ratio, of course, there is usually two stage reduction unit. There also one stage reduction unit is also used. Now, this is the input shaft. So, power is, this is connected to prime mover through which the power is coming to this pinion and then it is modulated to the higher torque with this gear, and finally, this is the output shaft. So, we have one input shaft, one output shaft. Now, this shaft is called intermediate shaft. So, in process of designing this gear unit, we shall learn how to design the gears, then we will consider that shaft. In fact, the shaft is cannot be rigorously designed, rather the size of the shaft will be dictated depending on that what will be the bearing. This is supported by bearings, and then so selection of the bearings, and then say we have to put the keyways, and finally housing. So, this is the bottom housing is shown, the top housing is open for this gearbox, top housing is removed. And if we consider this output may be a solid shaft or even it might be hollow shaft, as well as input might be also hollow shaft, but which is usually not, but in some cases the output shaft is made hollow. In some cases also that output is bidirectional, a shaft output is here as well as in this direction also. In case of hollow shaft also it is possible. So, this is a very basic idea about the gearbox, and in this housing on which this is half of the gearbox on which it is put. This is usually cast or even it can be made of fabrication, made by fabrication, that means welding. Now, in this picture it is shown a gearbox having the welded structure of housing. This is the welded structure of housing, okay. And in this case it is not a split one, this is not a split one, this is a single gearbox, and it is possible that all the gears can be assembled from the side and top open. This is the top cover. Now, say for example, if we consider this is the input. Now, in case of input, what is done, that first the gear is put inside this, that blue cover along with the bearings, and the whole thing is put here. Next, so this is the input. Now, next comes this gear. So, this is an intermediate shaft, sorry. Now, in this case you can see this is the shaft and this is the pinion integral with this shaft, and these two are bearings and bearing covers, etc. So, gear is put here, and it is not possible that you can put this gear here and you can assemble. So, this shaft partially is put inside, then this gear is put from that side, and then this is assembled from this side. So, this is the first intermediate shaft. Next, this intermediate shaft comes, bearings are put, then this shaft with pinion comes, and this gear can be put from this side, and then this side cover is put, there is another cover. Finally, this is the output shaft, this is put here. So, this is a little complicated and not an easy task to assembly, but this is just shown that what are the gearbox, what is the reduction unit, and what are the components there, and design of such gearbox involves the design of helical gears, the design of shaft, design of bevel gear, design selection of the bearings, then calculation of the how much lubricant is required, all such things. For refined calculation you need to consider also this how much the heat generation, etc., etc. Now, the view of this is of course the cast housing, bottom housing is shown. In this case this is the not cast one, this is the fabricated one, but functionally this will have the first reduction here, bevel reduction. Next there is a helical reduction. So, this is one first intermediate shaft, this is second intermediate shaft, and this is the final stage where the helical gear and pinion set is there. So, this is just to give an idea what is a gearbox. Now, in our case we shall learn the design of gears, selection of bearings, finalizing the shaft dimension, etc., based on a problem. Now, here I have shown as if we are designing a two-stage gearbox, but the stage depend on what is the transmission ratio. So, this is a pictorial view of the gearbox. Already I have discussed, this is a 4-stage gearbox, first stage, second stage, third stage, and in front of that there is another stage is there. Here is another stage is there. Okay. So, this is a 4-stage gearbox. If we take a picture, it looks something like this, but what we are going to design, that is a 2-stage gearbox and with helical gears. So, it will look something like this. In the progress of these lectures, I will show how these gearbox are designed, and finally, we will also draw a gearbox of our design. Now, the problem is that which we are going to solve. A helical gear reduction unit has to transmit 30 Newton meter input torque at 1500 rpm with a total reduction of about 37 to 40. Now, first of all, we have given a specified torque which is 30 Newton meter. Now, that depends on at the end how much at the output, how much torque we need and what is the prime mover we have, or depending on the output and their load spectrum, we have to select the what should be the input torque, input power of this prime mover. And very often what is the nominal torque and what is the torque and power at stable condition, that is simply a base data, and our motor is of, or prime mover is of higher size, because we may need high starting torque, we may need additional torque during the power transmission, during the operations. So, that is why the prime mover may be of higher power than nominally what is required. The question is that for designing the gear, shall we consider the nominal torque or shall we consider the higher torque depending on the what is coming from the prime mover. Now, that is decided depending on the load cycles, and that is usually specified by the manufacturer, or sometimes it is the designer's experience. But in this case, we have specified that we are going to design, we are considering the nominal torque is 30 Newton meter. Now, for designing the gears, we may multiply that torque with a value depending on what is the amount of shock or starting torque is there. Now, here it is specified that input RPM will be 1500. Now, reduction ratio, instead of taking a fixed reduction ratio, we have given 37 to 40. Why it is given like that? In normal cases, industrial operations, plus minus 5% variation for exact what value we need, this variation is acceptable. Reason is that in any case this prime mover also may give plus minus 5% variation, or the whole purpose will be sharp even if we take plus minus 5% variation. However, we can always specify here that the reduction ratio should be such, but the reduction ratio is the ratio of teeth number, and it may not be possible that always we arrived into exact number. Anyway, let us look into the other part of the problem. At starting, the torque may go as high as 200%, and also there is medium shock loads during operation. This means that what the nominal torque we have considered, that must be multiplied with some factors, so that the design gear that can sustain at 200% starting torque and whenever some shock is coming. The material for pinion is EN 19A, and for gear wheel it is EN 18A. Now, I would like to mention that EN, that is the British standard, emergency national. In our country still we follow these numbers, but it has the Indian equivalent. When we will come to the design, I shall give you the exact equivalent of this material. EN 19A, this is a forged steel with alloy steel and it is very good for gears, and EN 18A, that also can be forged, but that also can be used for casting. The gearbox may be an ordinary industrial class unit, preferably with uncorrected gears. So, we are going to design a uncorrected gear sets. It is of continuous duty with medium shock as already mentioned, and overhauling time is 2 years. What does it mean, overhauling times? Now, two words are associated, one is maintenance, another is overhauling. Maintenance of gears means you have to look into the gearbox whether oil is properly filled or is there anything, something is going wrong in the gearbox, whether bolt is properly tightened even if after operations. In case of say for example, rolling mill, you will find the gearbox, the foundation bolt almost every day it is tightened. In case of general purpose, it may not be required. For inspecting the lubricant, you need to check through the window that whether lubrication is there or there is leakage. Sometimes if necessary, you can also one can observe whether any debris has come inside the lubricant also. These are the part of maintenance, but overhauling means after certain time you need to change some components of any machines. In case of gearbox, usually all bearings are replaced and seals are replaced, and if necessary that some other worn out components or which is highly stressed or damaged, that should also be replaced. But main things are there, bearing and seals will be replaced after certain time, and this is required to have the better life of the any machines. This means also that what should be the life of the bearing while we are designing. Now, 2 years means what it is. From this we have to know that in a day how long this machine will run, and in 2 years what will be the total running time. That is again from the application of the machines. That is why in some cases we can say the bearing life should not be below 10,000 hours. So, bearing should last 10,000 hours. And what is the life of the bearing? Life of the bearing is that it on the process it will be worn out. So, at some point gradually it will become loose, and with the as it wounds out, the dynamics of the gearbox will increase. Nowadays, there is a process is called fault diagnosis, by which we can say that how much vibration is coming, and from there we can identify that what should be whether we should replace the bearing or not. But in normal cases it is specified after say 10,000 hours or 5,000 hours you can replace the bearings. That means, beyond that point the dynamic condition will be more worse. So, we must replace that. Now, with this given data, now what are the design steps? What we should do now? In first step, we should the selection of stage, gear ratio and teeth numbers. In first stage, we will consider this. Next, in step 2, we will consider we will design the gears, and then third step we will make a first layout. In that layout, the gears will be drawn and the center distance will be finalized and shape of the shaft will come next. So, rough shape of the shaft is given in 4th stage. Then 5th step is the bearings are selected preliminarily, and then after putting the bearing in layout, load calculations become possible. Now, unless we do not put the bearing here, we do not know how much load will come on the shaft, what will be the bending moment and what will be the load on the bearing. So, first of all we have to select 2 bearings from the experience, and that we have to put at 2 ends, and then from there we know what is the where is the support and where is the loading point. We will calculate the bending moment of the shaft, load on the bearing, and then we will in step 7 we will do lives of the bearing, that will be estimated, and finally we will check the if estimated lives are not satisfactory, then a new set of bearing are chosen. Selecting a new set of bearings means either we have to go for higher series of bearing if it is a rolling element bearing, and in that case higher series means the inner diameter of the bearing will remain same, but the load capacity will be more, or we may need to increase the diameter of the inner diameter of the bearing, that means diameter of the shaft also, that means we have to alter the design. That amounts that the gear design may need to be altered. That means, suppose we have taken 17 tooth with 2.5 module, but we may find for that gear, that pinion is usually will be integral with the shaft, and we may find that whatever the diameter we are getting at the bearing end, that is not sufficient for the bearing life. So, we increase the module, we increase the shaft diameter, and we go for a new set of bearing. It is not possible that by a single calculations starting from step 1 to step 8 we will reach into a good design. We may need to change the gears design after the first calculation. Okay. In step 1, knowing the direction of input and output transmission ratios, type of gears, teeth, numbers are selected. Okay. Rules and limitations is that stage ratio not more than 6. Usually, particularly in the first stage, by no means ratio should be more than 6. Now, number of teeth should be again above the critical number. Then normally say if it is a if it can be managed by the spar gears, say for example, this type of gearbox we can manage with the spar gears, but normally straight tooth spar gears are not chosen because the helical gears have better performance with more or less same sizes. The two difficulties, one is the complexity, a little bit complexity in calculations, that is not difficult with the modern techniques, as well as for the designers it absolutely there should not have any problem. As such the manufacturing is concerned, this is also not difficult. So, helical gears are chosen instead of straight tooth spar gear, and we consider the formative number of teeth is equal to z dash by z by cos cube beta, the actual number of teeth by cos cube theta, and z being the actual number of teeth, and beta is the helix angle, which is normally taken 12 to 20 degree for single helical gear, and as with 20 degree involute. Z minimum number of teeth, that is ZC is 17. So, we consider the formative number of teeth in case of bevel gears would be 17. That means, if we consider 12 degree to 20 degree means 16 to 14 teeth we can take easily. Okay. Whereas, in case of straight tooth spar gear, if we consider 14, there will be undercut. Considering cutter's geometry, speed of gears and manufacturing methods, this number may further be lowered. Now, here it is again shown that what may be the photographic view of the gears. So, this is a typical view of a photographic view of a gear in the stop open, and as I have shown in the drawing, it will something look like this, where the Z 1 is the number of teeth in first stage pinion, Z 2 is the teeth number of gears in first stage, Z 3 is the teeth number of pinion in second stage, Z 4 is the number of teeth in second stage of the gear, number of teeth in second stage. And now, we will select that the transmission ratio, it is 37 to 40 it is given. In choosing the numbers of teeth and stage ratios, not only the size optimization is considered, but also roundness in center distances with uncorrected gear is taken care of. Normally, I would say that when the gearbox manufacturer who are manufacturing standard gearbox, sometimes they offer the gearbox what is available with them. In that case, the center distance are specified, overall size of the gearbox is specified, center distance usually multiple of 5 millimeter. Now, with uncorrected gears, to make the center distance multiple of 5 millimeter, we have to choose the helix angle number of teeth in such a way that should be within limit as well as that should satisfy the center distance. This is one part. Second part, while we are selecting the number of teeth, then usually a stage ratio should not be a whole number. Say for example, Z 2 by Z 1, the first stage ratio, that should not be whole number. Whole number means that the after say it is 3, that means every after 3 revolution same pair of teeth will come in contact. For that type of contact, there will be increase in dynamics, because if there is an error every after 3 cycle, that error will be propagated, and it is called tooth haunting. To avoid that, usually the ratio is made fraction as much as possible. So, with this idea, with these limitations, we shall consider that this will be of 2 stages, because if we 37 and if we would like to take the 6 is the limitations in the first stage, then what we can do, 6 into 6 point something will very close to 40. So, we can go for such a ratio, but the problem is that if we take that ratio in first stage and second stage where the torque is more, then you will find that gearbox size will not be optimum. This gap will be more and it will be big one. So, we take first stage it is less and second stage is slightly higher. In this case, what we have taken, that Z 2 by Z 1 81 by 17, which is 4.6, it is a fraction. So, tooth haunting is avoided and 17 is a good number, we need not bother about the undercut. So, 81 by 17 we have taken, and then in second stage we have taken 131 by 16, which is more than 6. The question is that if we do not take in second stage more, then more than 6, then we have to go for 3 stage gearbox. In 3 stage gearbox will be expensive. So, that is why for such a ratio it is very often we manage with 2 stage, and this stage is around this figure and other stage is this, say 5 then 8 should be a good figure, for which you will find that this can be optimum, but to keep our teeth number, our size within that, we consider this one, and then finally we find for that the transmission ratio will become 39.01, which is satisfactory. So, we can have the teeth number maybe like this. Now, next stage we shall examine for which what is the module is coming, and for which whether we can manage with a center distance which is multiple, at least multiple of 5 if not 10, that we need to examine, and if necessary then this teeth number again can be changed and we can go for a new ratio. So, for this part any machine design books will be good to understand this, but many informations are not available in standard machine design books, and also if a although the bearings and others can be selected from the internet or catalog, but if there is a ready made design data book in hand, that will be helpful. Okay, thank you.